You've probably heard that opposites attract. This comes from that idea has its scientific origins, at least in the idea of electric charge. Uh, Opposite charges attract while like charges repel. As you know, there are both positive and negative charges. If you have two positives, they'll repel each other. Two negatives will repel each other, while a positive and a negative will attract each other. Charge is one of the fundamental conservation laws. Charge can neither be created nor destroyed. And as far as we know, the charge of the universe is always conserved. So that's our last conservation law for the year that we'll have talked about. We talked about conservation of energy, although I guess conservation of mass energy would be more accurate to say. Conservation of linear momentum, conservation of angular momentum, conservation of charge. Those are the four conservation laws that we've touched on this year. There are more. You can look them up online, but some of them you don't have the physics to understand. So as you know, there are two charge-carrying particles that compose normal matter and a non-charge-carrying particle. The fundamental negative charge, of course, is the electron, and the fundamental positive charge is called the proton. And they each carry a charge of 1.6 times 10 to the minus 19th coulombs. The coulomb is the SI unit for charge. There are a couple different things written here. E is the constant. It is the electron charge. E is defined to be 1.6 times 10 to the minus 19th coulombs. So a proton has charge positive E, an electron has charge negative E. Q is the variable that is generally used for charge. I don't really know why, but it is. Electrons, as far as we know, are fundamental particles. There is nothing smaller that we have found that electrons are made of. Protons, however, are not fundamental particles. They are made up of quarks. There are 6 different types of quarks. Protons are composed of 2 different types. Neutrons are also, you also know about neutrons. They have 0 charge. Their mass is pretty close to the mass of a proton. And you also know protons have much greater mass than electrons. They have the same charge, but the proton has much greater mass. A guy named Millikan did an experiment. We know it now as the Millikan oil drop, 1909. He showed that charges in nature are quantized. And that's based on the idea that this is a fundamental charge, so that all charges come only in multiples of 1.6 times 10 to the minus 19th coulombs. So for a while, people, even after charge was discovered, we didn't realize that because you can only measure charges, and when you get to charges that are bigger that could be observed at the time, if you get something that's a charge on the order of, say, 10 to the minus 6th, then you wouldn't notice that it's in these discrete quantities of 1.6 times 10 to the minus 19th. It would just look like it's a continuous pile of charge. But Millikan measured fundamental charges, and he found, in all of his experiments, he found charges that were 1.6 times 10 to the minus 19th. He found charges that were 3.2 times 10 to the minus 19th, 4.8 times 10 to the minus 19th, and so forth. But he didn't find any that were, for example, 2.0 times 10 to the minus 19th. And that's because charges only come in multiples of 1.6 times 10 to the minus 19th coulombs in nature. As I mentioned, protons are made up of quarks that have charges that are a fraction of this, but quarks do not exist by themselves in nature. They always come in threes and make up different particles. Although I just read recently that they've created they've synthetically created in the particle accelerators and whatnot some 4-quark particles. But naturally they come in threes. And charges naturally come in multiples of 1.6 times 10 to the minus 19th. So if we have a charge, say we have a charge of, I don't know, 3.5 coulombs, we could divide that by the electron charge, 1.6 times 10 to the minus 19th, and then get the number of excess electrons or protons on an object. And I say excess electrons or protons because most macroscopic objects have about zero net charge because they have an equal number of protons and neutrons. Objects can be given a net charge when they transfer electrons. For example, you may have, I'm sure you've seen this at some point, if you rub a balloon on your head, that causes electrons to be transferred. The balloon gets a negative charge, your hair gets a positive charge. What happens? Well, you know this, your hair sticks to the balloon. That's because electrons have been transferred, from your hair to the balloon, and therefore your hair has a positive charge, your balloon has a negative charge, so now they attract each other. And then if you remove the balloon, now what happens? Well, now your hair sticks up. Because the different strands of your hair each have a positive charge, and so they repel one another, which causes your hair to stick up. In your textbook, page 655 has a table showing how strongly objects hold onto electrons. So some materials tend to keep their electrons more than others. When you rub two objects together, generally some amount of charge will be transferred. Some amount of electrons are what are free to move in atoms generally, more so than protons are. So in that table, materials near the top of the table hold on to their electrons less strongly than materials near the bottom of that table. So if you rub two materials together, the one that's lower in the table will take electrons from the one that's up higher in the table. And that charging by rubbing is called triboelectric charging, just so you know. Charges tend to be pretty small, so we frequently use these particular metric prefixes. We've touched on them before, but we haven't used them a ton. This mu stands for microcoulomb, and a microcoulomb is 10 to the minus 6th coulombs, 1/1,000,000th of a coulomb. NC is nanocoulomb. N stands for nano, which is about 10 to the minus 9th coulombs. That is 1/1,000,000th of a coulomb. And we'll use these prefixes pretty frequently throughout this unit. Just a random fact: lightning bolts are happen because of charge buildup during storms. There's a lot of charge that builds up on one surface, and those electrons then are attracted to the charge tends to spread out pretty evenly, and so when there gets to be enough buildup of charge gets transferred. The lightning bolt transfers charge from ground to cloud or cloud to cloud. And typically lightning bolts have about 20 to 30 coulombs of charge. So lightning bolts are the most chargy thing I can think of, and 20 to 30 coulombs is how much charge they transfer. So typically things involving charge have much less charge.